started. I hope you're all ready for another exciting afternoon. Short one, because today's Wednesday. All right. Good afternoon, everybody. Welcome to another afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. And I have exciting news for you. If you checked your email or looked at the announcement, I posted an extra credit. And that extra credit project is optional, but if you do it, it's worth 10. Yes, 10 points. Let's take a look at the extra credit project. And if you look on D2L or your email, you'll see extra credit project, 10 bonus points. What do you have to do to get your 10 bonus points? Well, you have to create a chart that contains 10 organic molecules found in the ingredients list of commercially available molecule or products. In other words, things you could buy. And you can use a molecule only once in the chart, but you can get up to 3 molecules for products. That's my way of making you look at a couple of things. To get full credit for that molecule, which is 1 point, all entries in a row of the chart must be correct. For each entry, record the name of the product, the name of the molecule you're interested that you're pointing out from that product, and one of the functional groups in that molecule, if there's more than one functional group, or the only functional group present in that molecule. Be sure you put your name on the chart. It should look like the following: product, molecule, functional group. And I took brand X wine, has ethanol, and that's an alcohol. All right, to make it interesting, you cannot use the molecules sucrose, ethanol, isopropyl alcohol, also known as 2-propanol, acetone, ethyl acetate, propane, or acetic acid. You can't use the following products: beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, or butter. Everything else is fair game. Now, this is very important. Ingredients must appear on an ingredient list on the product. Also, they must contain a functional group that we discussed in this class. When students go to functional groups that we didn't do, they always get it wrong. So I've eliminated that problem for you. Now, what I mean by ingredients must appear on an ingredient list of a product, well, you can say a certain ester is responsible for the smell and taste of bananas. But the last time I looked in the supermarket, bananas where I shop don't have ingredient lists on them. All right, important thing. This is due by the end of the day, December 3rd, 2020, which is test number 4. No late projects are accepted. It got a little out of shape here. Please upload it as a PDF or Word file. I have it set up in the assignment area. Now, this is an optional project. You don't have to do it. But if you do it, you get 10 points. That's like adding 10 points to your total. Well, it does add to your total, but you might want to think of it as like getting 10 points more on any test, which is a good thing. Now, couple things. Beware, not all names on labels are IUPAC or common names. Simethicone, which is a trade name, is not a ketone. You'd say, oh, and the ending, no, it's a silicone product or compound with silicone. Now, how do you find out about your structures? Use Google or use your instructor, me, to check structures. Now, for Google, place the name of the chemical in the search box and type the phrase chemical structure. I have found within the first 2 or 3 web pages, you will open up a page that has the structure of your molecule. Now, how do you use Dr. White? Me? Well, once you got your list made up, and it doesn't have to be formally made up, but you have it, email me it, and or see me after class or in my office hour, and I'll check it and I'll tell you what's right or wrong. And that way, make sure you do that with me way before December 3rd. You'll have plenty of time to uh, do your project. Remember, this is an individual project. You shouldn't be working with someone else. I've had students try to pull a fast one on me by, oh, I'm working with so-and-so, and we just changed the order. No, that's called cheating. Now, let's see how easy it is to get at least 1 point real quick. One of my favorite products this time of the year, Carmex, and you put it on your lips. Now, let's do an experiment. Nah, it's not working. But if you could read this, you'd see one of the ingredients on here is phenol. And what does phenol have? 2 functional groups. It's an alcohol, and it's also an aromatic compound. So you could put down for Carmex, you get up to 3. There's other stuff on the label. I'm not going to give it away. But one of them would be Carmex, phenol, and then alcohol, or Carmex, phenol, benzene ring, or aromatic ring. And you can get 2 more from here. There's, if you go, by the way, you don't have to buy anything. Normally, if I would tell people, but in today's environment with the pandemic, I'd normally say, go to any supermarket or big box store, walk around, pick some stuff off the shelf, and look at the label. Or better yet, take your cell phone, take pictures of some labels, and go home and look at them. Now, where can you find good stuff? Well, try your bathroom, all your personal care products, shampoo, soap, etc., or look in your kitchen. Things in cans, look in your refrigerator, things like that. Now, a common misconception that I don't know why it is, and I'm going to stop it now, is you need 10 different molecules and they all have to be different functional groups. No, if you want all 10 to be alcohols, that's fine as long as they're 10 different molecules, up to 3 molecules per item. So that means you got to look at 4 things because 3, you got maybe more too. And it's my secret way of teaching you, oh, look, the stuff in here, that's organic chemicals. Most people see ingredients and forget those are chemicals. And that's my extra credit bonus project. It's 10, yes, 10 bonus points. Any questions? All right, well, in that case, let's move on. Now, on Monday, I went through chirality. Ooh, that reminds me. All right, important announcement, public service announcement from me to management. And that is on Monday, I will go through the lipids, otherwise known as fats and oils, problem set. I'll give you plenty of time to work on it. And yes, we do have class next Monday. And I believe we also have class on Wednesday. Let me check something real quick. Hold on. They still do it. All right, next Wednesday, right before Thanksgiving, ECC is open until 5 p.m. Our class starts at 1. We'll have class next Wednesday. It's a short class like today. And but please do show up if you're out. Well, hopefully you're not traveling, not in this environment, but if you are, don't forget I post all my classes on uh, YouTube, my YouTube channel, Chem 170. All right, and on Monday, I talked about chiral and achiral objects. Remember, chiral is an object that has a non-superimposable mirror image, and achiral is some object that has a superimposable mirror image. Did all of you do your homework project? That was take your right hand and put it in front of a mirror, and what do you see? Your left hand. And you see this? What's that? Spider doing push-ups on a mirror still. Ooh, athletic spider. Oh, that was lame beyond lame. All right. I talked to you about chiral centers, otherwise known as chiral carbons, and we talked about other things. Talked about enantiomers, which are non-superimposable mirror image. I showed you how to do that. Talked briefly about diastereomers, showed you, but it'll not be on test. Fisher projections. Talked about DNL designation, not on the test or final. And also optical activity, physical properties of enantiomers, not on the final. All right. Thought I had you on screen. Now let me check. Everybody see back to chapter 16? Thank you. All right. Switch is off on here, but there are a few things you should know. One, there's certain classifications. If a monosaccharide has an aldehyde, it's called an aldose from aldehyde. And this won't be on the test, but for other classes, you might need to know this. So that's why I'm going over it. When a monosaccharide has a ketone, it's called a ketose. Now, if you know anybody who's diabetic, one of the things they have to watch out for, a very serious problem, is ketosis. And that's when they have certain sugars with ketones. Now, what was it? I think 2 or 3 summers ago, I forgot which, I had 2 students who were both diabetic, and thanks to modern technology, they had on their arm the little insulin pump, which made their life a lot better, as opposed to having to either inject it or the old big ones. I had a student like that too. I've had a lot of students, which makes Dr. White happy. All right. Now, something you should know, what is a sugar? We use that term in our daily life, and that's a designation for a mono or disaccharide. What's a sugar? You should know, mono or disaccharide. Tonight at midnight, I'll be giving speed note-taking lessons. No, I won't. All right, let's go next. Remember, if I go too quick. Now, turns out there's something very important that monosaccharides undergo, and that's the cyclization. And I'll talk about that in a little while. But let's look at this structure right here. And I'd just like to cover real quick that D-glucose, which is this compound right here, turns out it's the most abundant sugar in nature. And it's the sugar found in our blood. That's our blood transport carbohydrates. And it's an aldohexose. This switches off on this slide right now. Aldehyde, 6 carbons, 1, 2, 3, 4, 5, and 6. And it rotates plain polarized light to the right, which you have to do the experiment. You can't look at the structure to see that. So this is D-glucose. Now, this is D-fructose, and again, for both D-glucose and D-fructose, I'll never ask you to draw the structure on a test question such as draw the structure of D-glucose or D-fructose. That I will never do. But you should still be familiar with the structure. Now, this has a ketone right here, carbonyl, carbon here and here, so it's a ketohexose. Hexose tells you 6 carbons too. 1, 2, 3, 4, 5, 6. And turns out D-fructose is the sweetest of all sugars available. And it rotates plain polarized light to the left, and it's found in corn syrup. In fact, our, what would you call it, corn syrup producers found a way to maximize the amount of D-fructose in corn syrup. And if you look at a bottle of pop, or if you look at a lot of things that are sweet, you'll see after water, you'll see either corn syrup or high fructose corn syrup. Decades ago, they used to use sugar, which I'll teach you is called sucrose, that sugar. And when they found how to do corn syrup and make it high fructose corn syrup, that's much cheaper than sucrose. Why? Because it's cheaper to make and you need a lot less because it's sweeter. And so all the industries shifted to that, because if you've ever worked in any place that makes things, when you lower your raw material costs, you, guess what, boost up your profits, which is always the important thing in any company. I'm not saying that's wrong. I've helped boost profits at companies, but that's why they switched from sucrose to fructose. Money, lots of it. And I'll talk a little later, not now, about how my personal feeling about, I don't know if you've heard, for a number of years, a number of mothers groups have said, D-fructose, that's causing major problems in our children, like autism and everything. I don't believe that, but I'll explain why later on. And fructose can form a cyclic form too. Now, this is called the Hawthorne projection. And at one time I tried to teach the students, and you could take 2 weeks with students and they still don't get it right. So I don't teach it anymore in my class, and I'll never put it on the test. See, I even have it on the slide. By the way, everybody see that on the test on the screen? Thank you. Now, let's look at a reaction of fructose, glucose, and then I'll do fructose. Now, it's an equilibrium. That means it shifts back and forth. Now, Dr. White promised you no new reactions. So let's look at something very important. An old reaction from chapter or test number 2. And you learned the following reaction. Keep your eye on the carbonyl carbon. If you start with an aldehyde or ketone, react it with an alcohol in the presence of acid, you get a hemiacetal, hemiketal, depending on what R prime is? Well, there's an acid catalyst, and this helps it make the reaction go faster. Now, there's two types of reactions you can think about. Those that are intermolecular between two separate molecules, or those that are intramolecular in the same molecule. Now, when you have an oh, by the way, this is the first time I've ever done this ever in a Chem 170 class. You guys put that down in your diary, dear diary. But anyways, I think it gets the idea. When it's in the same molecule, it's quicker and you don't need to catalyze it. When separate, you got to help them come together, and acid does that. So, I'm going to have to remember that. I'm ambidextrous. I'm also Awful Humor Wednesday. All right, now let's look at glucose. And it's in equilibrium with its cyclic form. Now, if you look right here, we have an aldehyde. And if you look at C5, remember 1, 2, 3, 4, 5, what do we have here? An alcohol. So in the same molecule, we have an aldehyde and an alcohol. And it turns out this can come and react like that. Now, as I said a little while ago, not that long, students couldn't master, and a lot of even chemists have trouble with Hawthorne diagrams. So how do you show that? Well, I came up with an idea, or don't tell any other organic chemists, but if we have the really world's ugliest looking cyclic compound, it's easier for students. So I'm going to show you how to do that. Everybody see the whiteboard? Thank you. All right. Now, do you break carbon-carbon single bonds? No. So immediately, I can draw this. What's ever not involved in the reaction won't change. Oh, by the way, the closer we get to Thanksgiving, the worse my hydrogens look. Now, the carbonyl carbon right here still has a hydrogen, and is this carbon now? Goes from here to here. So this will have a hydroxyl group. R prime is the hydrogen right here. Hold on 1 second. The hydroxyl group looks like it wants to run away. Or the hydrogen. There, that looks better, sort of. Now, here's this carbon. Now, where's our alcohol? Right here. And this oxygen right here becomes this oxygen right there. So I'm going to put it right there. And where is this bonded to? The carbon right here. So I'm going to make the world's ugliest, longest carbon-oxygen bond. Yeah, that's pretty long and ugly, but it shows the trick. And this cyclic form is made. By the way, Dr. White is going to be subtle again. Know this. If on a test I put for a reaction, give the reaction products for the following, and I give you this right here, the structure, I may or may not write glucose underneath, but you should recognize that this happens. Or on a test, I could give you this and say, give me the starting material. You should know this. Why? Because this is an important reaction. If this didn't happen, we wouldn't have any of the carbohydrates in our daily life. You wouldn't have, the good things like French fries, potato chips, Doritos. But on a more serious, we wouldn't have plants, we wouldn't have oxygen, we wouldn't have trees, we wouldn't have a lot of food for us and animals, because that all depends on that cyclization reaction, which I showed you just now. So is this important? You bet it is. And let me go through it again. Let me remind you, you learned for test number 2, aldehyde plus an alcohol acid catalyst gives you this compound, the hemiacetal, hemiketal. Now, since you're in the same molecule, the alcohol and the aldehyde, you don't need the acid catalyst, and we don't have it here. Now, this alcohol reacts with that carbonyl carbon to form this right here, but here. And this whole thing right here is my R prime. This hydrogen, or our double prime, the hydrogens are prime. And here I have the hydroxyl group, and this oxygen, this carbon are this R group. And that's how you do it. Now, I always forget the structure of fructose, so let me cheat. Now, the same thing can happen with fructose. And this is fructose. Sweetest sugar around. And up above, I'll remind you again, the reaction you learned for test number 2. Take an aldehyde or ketone. In this case, we have a ketone. It's right there. And react it with an alcohol and acid, and turns out the same C5 alcohol in fructose will react. C5 means carbon 5. 1, 2, 3, 4, 5. Remember, carbonyl always gets the lowest number. So in fructose, the carbonyl carbon is 2. But I'll never ask that on a test. And as I showed you earlier, you get a hemiacetal or hemiketal. Keep your eye on the carbonyl carbon. Becomes this carbon right here. And this also is in a equilibrium. Whatever is not changed, I'll write the same. This I will change. And this hydroxyl group will attack that carbonyl just like this attacks that carbonyl to form this bond here. So once again, I came up with the idea through the world's longest, ugliest, and this carbon here is this carbon here, and this bonds to that carbon. And notice on that carbon, you'll have a hydroxyl group, and that's the cyclic form. And this is a lot easier to see than the Hawthorne projection, which I know how to do, but I don't expect you to. And once again, I'll be subtle. Hint, know this. What do I mean by that? If I give you this molecule and this equilibrium on a test, give the organic product or products, you should know how to write this. If I give you this plus the equilibrium and ask, give the starting material, you should know it's this structure right here. And this is important too, because if this didn't happen, we'd never have table sugar, sucrose, because this is an important part of making table sugar sucrose. Now, next week on Monday, I will repeat this again because it's so important. But let's go through it once more. For glucose, remember ketone or aldehyde, in this case aldehyde, alcohol and acid, since it's intramolecular, the hydroxyl group is in the same molecule with the aldehyde. You don't need a catalyst. The hydroxyl group on C5, the one right above CH2OH, same for both fructose and glucose, attacks the carbonyl, forms this long, for my structure, carbon-oxygen bond, just like right here. And on that carbon will be a hydrogen and a hydroxyl group. And if we look over here for fructose, same thing happens. Aldehyde or ketone, alcohol, acid catalyst. For intermolecular, inter means separate molecules, but when it's intramolecular, in the same molecule, you don't need a catalyst, and you have this equilibrium. This will now attack that carbonyl, just like this alcohol attacks the carbonyl, forms this oxygen carbon bond, opens it up to an alcohol hydroxyl group, and the same thing happens. And the way to show it is, for you, easier way, this long carbon oxygen bond, and this opens up to the hydroxyl group. Both of these, know them, please. Are we doing time-wise? Good. Oh, I got to do this on the board. So I better get back to my whiteboard. And let's talk about reductions. And again, Dr. White's keeping his promise, no new general reactions. Now, back in test number 2, and let me just check. Everybody see the whiteboard? Thank you. All right, back for test number 2, I taught you to take an aldehyde or ketone, add hydrogen, a catalyst. Guess what? You get an alcohol. You break the pi bond to the double bond, just like you learned in a carbon-carbon double bond, but now we have a carbon-oxygen double bond, and each atom of the double bond gets a hydrogen. Well, let's do that with glucose. Now, alcohols will not react with hydrogen, the catalyst. You know something? I've hogged all the fun today. I'm going to let you have some fun. What would be the organic compound or compounds, product or products for the following reaction? Have some fun. And when you're done, give me a thumbs up. While you're doing that, I'm going to sneak some tea. All right, I think everybody's done. Remember, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Oh, look, right there, I have an aldehyde. And I'm reacting it with hydrogen and a catalyst. Well, anything that won't react with hydrogen and a catalyst stays the same. So I'm just recopying what I had on the left here. Now this carbon right here is this carbon right here, which becomes this carbon. So the hydrogen is still attached, and I'll break the pi bond, and I'll get this. You might want to think of that as CH2 or like that. Now, turns out this molecule has a name, and a common name besides the IUPAC, and the common name is sorbitol. I'll never ask you what sorbitol is, but let's go out into the real world. All right, can everybody see sorbitol from Wiki? Thank you. Now, sorbitol has another name, but it's a sugar alcohol. In other words, it's got a sweet taste to it. Your brain thinks, ooh, that's sweet. And it's made from the reduction of glucose. What does reduction mean? Add hydrogen to catalyst. Now, let me move this up. You look over here, here's the structure. You have 6 carbons. Every bend in the line is a carbon. 1, 2, 3, 4, 5, 6. And each one has a hydroxyl group. And if I were to go back to our, remember, each intersection of a line is a carbon. 1, 2, 3, 4, 5, 6. And each carbon has a hydroxyl group. So you just learned how to make sorbitol. Now, sorbitol is made from potato starch where they get the glucose, but where is it found? It's a sweetener and it's also a thickener. Now, it can be used as a laxative, but the place you're most likely to find it is in over the counter. They don't show it here. Over the counter um, products like cough syrups and things like that, those types of over the counter medicine. If you look at a bottle of cough syrup or some cold, syrup that, relieves the symptoms of a cold, which you hope is not COVID. But anyways, these days, ah, anytime I get a runny nose, oh, hope I don't. But anyways, back to normal times, hopefully soon. But if you look at a bottle of cough syrup or something like that, you'll see at the bottom, it has sorbitol. Now they put that in there for two reasons. One, it makes it sweeter. If you're trying to give medicine to a kid, no, oh, it tastes good. I'll take it. They make it sweet. The other thing is you've been conditioned. The thicker something is, the better. Ooh, this is not like water. It's a little thicker. That must be good stuff. And sorbitol is very thick, like molasses. And by putting it in there, they can thicken it. By the way, to thicken something calls increase the viscosity. Viscosity is a way of measuring how thick it is. The higher the viscosity, the more thick it is. Dr. White's worked with that stuff in industry. And I've measured viscosities, and then also I've had people do it for me once I became a manager. So that's sorbitol. And now you know sugar, glucose, can be made into a number of things you find in your daily life. Now, if I look at the clock, we're just about done for the lecture part. So, excuse me, I'm going to do something that I hope you can survive. Let's go right into the lab. I'll get you out real quick. We'll be out in about 10 minutes, as opposed to me saying, I'm going to take a 5-minute break to stretch. This way, well, I'll get you out early. Shh. Okay. All right, everybody, put on your gloves. If this one you don't need your gloves, put on your safety goggles, and we're going to do today's lab. Now, hopefully, you see on your screen light dissolves light. Everybody see that? Good, thank you. Now, I've taught you when we talked about how soap works, there's an important rule of thumb named light dissolve light. Now, a rule of thumb means it's true about 95, 98% of the time. If it's a law, it's always true. This isn't always true, but I'd say almost, not totally, but almost it's true. And light dissolves light describes polar substances are soluble in other polar substances, and nonpolar substances are soluble in nonpolar substances. And if you mix opposites together, polar and nonpolar, they're not soluble. So goes the rule of thumb. Now, if we're at ECC and you're about ready to go in the lab, I tell you, today's lab, you can find out, is Dr. White lying to you about this? And that's the beauty of science, especially chemistry, and especially organic chemistry. You want to see if something's true? You go into the lab and prove it. You test it. And that's the basis for all science, which is one of the reasons I became a scientist, because you don't just guess things, you prove it. By the way, one company, one of the biggest slams you could say to someone in a meeting was, yeah, That's a fact. That's the truth, and it's a fact too. That was Axel. We used to say that all the time. There's this great engineer who taught me a lot of stuff about working in chemical plants, and that was Chuck Wilhelmy. He was older than me. I don't know if he's still alive. I haven't seen him in decades, but maybe he is. Great man, taught me so much. All right, now, when we talk about polar things, water is the most polar substance in our world. Water is polar. Now, for this lab, if you were in ECC, and I have the data in here, you would use also hexane. Hexane is nonpolar, similar to gasoline, which is nonpolar. In this lab, you will determine if various substances, such as products you use in your daily life, are polar or nonpolar. This will be accomplished by determining if these substances or products are soluble in water, you'll test, and in hexane. And soluble means you have a homogeneous solution. Insoluble means it's not homogeneous, it's more than one layer. Now, how many of you ever had, assume this is a bottle of oil vinaigrette dressing. You go like this, put it on your salad, put it down, look at it 5 minutes later, and you see 2 layers. That's because the top layer of oil vinaigrette dressing is either vegetable oil or olive oil. The bottom layer of oil vinaigrette dressing, vinegar, is mainly water. So you've got polar and nonpolar. By the way, there's all water in there. That's why you don't see 2 layers. It's good water too. And anyways, that's how you tell. So for today's lab, remember, hexane is flammable. Put all waste in the waste beaker and never light any matches or lighters in an organic lab. Now, what you'll do is put a little DI water. DI means deionized. That's pure form of water than what you get out of your tap in your kitchen or bathroom. And add 10 or so drops of the liquid. And then you'll mix it. Now, by now, we've done a couple labs, and let me see if I have some. What is it? No. All right, assume this is a test tube. Here's the top, you pour things in. What I tell students is never, ever shake a test tube like this, because you can get chemicals on yourself or someone nearby. Now, there are 2 ways to stir a test tube if you're ever going to do it. One is hold it firmly in one hand, take 2 fingers, go 1, 2, 3, 4 times. If you're in the mood, 5. Don't tickle it, that won't mix it. And that's one way. And the other thing we have in the labs, which is really cool and students like, and Dr. White does too, it's called a vibro mixer. It's got a little rubber circle and a motor underneath, and Dr. White's going to sneeze. It's a slow developing sneeze. I think I stifle it. Anyways, you take the test tube, hold it firmly, you push down, and it's got a switch when you push it down, and this starts vibrating real quick, much quicker than I can do it, and it stirs your test tube. Those are fun. Students like doing that way better than this way. And that's how you do it. And you put it down, let it wait a minute or 2, and see if it's homogeneous or heterogeneous, 1 layer or 2. Now, it turns out I have the whole chart. Now, in this one, you do not have to draw structures. And notice we do things like acetone, baby oil, ethanol, ethyl acetate, isopropanol, otherwise known as 2-propanol, octane, sodium chloride, starch, sugar, vanilla, Vaseline. I have people do this in a beaker because it's hard to clean that out of a test tube, and vegetable oil. And notice I gave you the results. Is soluble, yes or no? In part 2, you'll repeat the same thing you did in part 1, but instead of using water in the test tube, we'll have hexane. And you put about 1 or 2 milliliters of hexane. This is one of those labs, you don't have to be exact, about a third of the test tube. And then you'll put some of each of the things you're testing. And you'll mix the test tube, like I said, and see if it's soluble. And by the way, part 1, part 2, put all substances afterward in the waste beaker, which I would have out. And once again, you're testing the same things, but now in hexane. Now, to have fun, I did a part 3. We're mixing a few separate things together just for the fun of it. Lab should be fun. And same procedure, put some of whatever one item in, then put some of the other, and mix it and see if it's homogeneous. And some of the things we tried were, which you normally wouldn't do, but it's still fun, baby oil and vegetable oil, baby oil and starch, vegetable oil and starch, vegetable oil and Vaseline, and ethanol, vanillin, and then water. Now, this one right here, I should have put moderate yes as opposed to this yes, but it's okay with yes the way it is. And then for today's lab, you'll answer these questions and hand it in next Wednesday. Any questions about the lab? Well, aren't you glad I didn't take a break? Because guess what time it is? It's time for me to say goodbye. I hope you had a nice day with me today. Don't forget, Monday, I'll go through the fats and oils problem set. And we're on track with the syllabus, which is a good thing. And if you notice, I haven't had the rush to catch up. By the way, catch up, you can find some good things for the extra credit in the ketchup bottle. Oh, I gave that away. Shucks. But anyways, with that, I'm going to say, gang gesund, be healthy, be safe out there. Don't forget to wear your mask outside and wash your hands a lot. I wear rubber gloves when I go out. Supermarket, you can get them. If anybody's interested, send me an email and I'll give you the link on Amazon. These are nice, heavy, disposable, but they're so thick. When I come back, I take them off, let them sit for 5 days because the virus only lasts 3 days on any surface. After 5 days, they're clean to use again. But anyways, gang gesund, be safe. I'll see you on Monday. Bye.